Hey, what's up, guys? So in this video that I want to quickly introduce this for a series and Dirichlet kernels. So this is similar like in this previous video that okay. So the continuous version, right? So let me just quickly say about it. So in the continuous version that you need to show you prove so-called Fourier transform. So let me just write it. So given any f that you can define of this kind of thing. And this is called a Fourier transform, that's so-called frequency domain. And you are learn about the inverse Fourier transform, just do the same thing. Just you just put this and to do this I omega t, but this time instead of integral of omega, and you times some let's say 1 over 2 pi or something. Or it should be 1 over pi. Okay. That should be 2 pi. Okay. So so this kind of thing, right? So this if you believe so-called Fourier transform makes sense, that this will be f of t. And in order to prove it, as I previously showed, that actually these two will give you the following weird identity. It says 2 pi delta omega is basically some exponential I omega t dt. Okay, so the key idea is to prove, if you can prove this, then you prove the Fourier transform in actually makes sense. Okay, so in this video that we are going to describe the sensing in the Fourier series. But the situation is more complicated. You need a lot of work. Okay, so this is seldom talk in yeah, this is seldom talked about in engineer mathematics. Okay, so let me just oh oh okay, I should remove this. Oh, it's fine. Okay. So let me just quickly remind for a series. Uh, sorry. Maybe I use this. Okay. So remind for a series. Right? So if you believe if you have a function, let's say from negative pi to pi, a real number, and you say that this is periodic, then your professor tell you that you can write this f view as a theta, right? Theta you can view as on a circle, right? Because now this is periodic, right? So I can map into a circle, it's fine. So it says that f of theta should be can be written as trigonometric function, right? So it is Cn exponential I n theta, and from negative infinity to infinity. Okay, and the Cn, so this is basically the Fourier coefficient, and this is the Fourier series. It's obvious that this is well defined as this is natural because exponential I n theta has a period 2 pi. So this is very natural. But let's say you believe this is true, right? Suppose you believe this is true, then this would immediately implies that so-called so if this is true, then you can write down the Cn, right? So naturally, you can write down Cn as 1 over 2 pi, 0 to 2 pi, and f of theta is exponential minus I n theta d theta. Okay, and this is basically using the orthogonality relation. You know that 0 to 2 pi is exponential I m and minus theta. Right. And the integral with d theta is actually the 2 pi times delta mn. Okay, so this means that right. So if you know this is true, if this is trivial to prove, right? This immediately implies that all is Cn to be this. Right, so this is usually somehow like for a series that people already described, right? So it says, oh, it's fine, right? And right, so you start to do a lot of like example, right? Somebody give you f, and you just try to do some integral and find this all this coefficient. Okay. And you will also tell people that, oh, if I give you a bunch of Cn, which is somehow symmetric, that you can reconstruct F, right? So, but here's the question. Okay, so the question is that is this true, right? So if I give you Cn, if you start with F and you get Cn and you plug Cn back, is this indeed give you the same function F? Okay. So this is somehow like seldom taught in the textbook. So let me just write down what I'm saying. Okay, so if you are saying this is true, right? So what are you talking about? You are saying that, oh, if I write my f in terms of, let's say, Cn from infinity to infinity, exponential I n theta, then somebody tell me that, oh, Cn is actually has a beautiful formula which come from also a negative relation. So let's say this. Okay, so I can plug it back, right? So I should get something like this. Let me just write down, right? So 1 over 2 pi, 0 to pi, and so notice that theta is dummy variable. So in this part, I should use theta bar. Okay, I am bar, d theta bar, and this is plus I theta, and this is f of theta, right? So my question is that how do you prove this is true? Okay, so what you are saying is actually the following. You are saying that, oh, if I take 1 over 2 pi, I notice that I sum over is I do some like change of integral and summation. Actually, it's not doable in general, but let's suppose this is true. And you're doing this kind of thing, right? So it's in theta minus theta bar. And you write down as this 0 to pi. And you write down as this. Okay. So indeed, what you're saying is that, oh, right, this guy should serve as a delta function, right? So should serve as a theta, maybe theta bar minus theta. Or actually, yes, so or actually it's the same as theta minus theta bar. So if you believe it, if you prove it is true, right, then the integral of delta of the theta minus theta bar times f theta, f of theta d theta bar will give you f of theta, right? So the problem is that why this is true. So, so my question is the following, right? Why this is true? Why? Is it so obvious that this is true? So what I'm saying is that if you integral this, you do something like that, you get like 1 over like 2 pi. Is this is true, right? Can you like prove this is true? If you want to say, oh, if I want to prove this is true, then it's the same as plug it back, right? So the situation is much more complicated, right? So compared to the continuous. Okay, so in order to prove it, it actually needs some like more somehow like technical input. Okay, so the rest of the video is that let me just explain how to rigorously prove it. Okay. Uh, so let me just first do a simple things. I do change a variable, right? So indeed, I only need to prove the following. I only need to prove the following. So I just do a change of variable and I just do the simple case. I just do all the sum of. I just shift data to say my shift. Okay, and so the goal is to prove this is true. Okay. So as I say that this is actually not a simple functional identity because delta function is not a function, right? You need to do it in the integral sense. Okay. So in order to prove it, let me introduce like two simple results. The first one is the simple integral. We already show in it's basically in the continuous and the discrete one, which is famous, 0 to infinity sine x divided by x. This is pi over 2. And you can prove it using the complex integration. Okay, so I would say that's a simple results that you should know how to prove it. Just write the f of z and do the contour integral. And the second one may be a little bit difficult, it's called the Riemann-Lebesgue lemma. Okay, so this one tell you that if you give me some good function, which is continuous, I think continuous is enough. Okay, so it's continuous function from, let's say, AB to real. And then you do the f of x and cosine nx dx. And let's say A to B. and also maybe sine nx dx. So n is just a integer, right? And you do the limit of n, either n goes to infinity for sine or cosine. So this is also n goes to infinity, and this will be the same. This will just give you 0. Okay, so this is called Riemann-Lebesgue lemma. So this lemma just tell you that give me a function which you times a cosine or sine oscillation part if the oscillation is very uh, if the frequency is so high, then everything goes to 0. Okay, so the intuition goes as the following, right? So let's say this is f, and then let's say you times sine of sine, right? You times sine. So this will give you the oscillation. Maybe you do this, so it's oscillation. And then when this oscillation is very small, that all of this become like very random, so you should sum out to 0. Okay, so this is the intuition. And to rigorous prove it, you need to know some real analysis that you know. Let me just give you a sketch, right? So sketch. Okay, so this sketch basically just doing a simple thing, right? You know that let's say your continuous function, let's say f is continuous. So by Weierstrass approximation, I know that f can be approximate by polynomial. Right, so let's say so I only need to care about sk, right? So the only thing is to you just using your trivial mathematics, just prove that this is 0 for all k greater or equal to 0. Okay, so you just need to prove this is true for all monomial x to the k. And so this is just simple calculus, right? So and if you prove it, then you prove it because f can be approximated by arbitrary can be approximated by polynomial, right? So this is true. Okay, so once we have these two input, then we are gonna to prove it. Okay, so prove. So we need to using the same trick, right? So we need to write this guy, and then we do some like truncation. Okay, we do some truncation. Uh, hmm, we do some truncation, right? So let's do this. Maybe I change to m, and I add from m from minus n to n, and I will let n to be m to be infinity. Sorry, n to be infinity. Okay, so this is actually exponential minus I n theta plus minus I n minus 1 theta up to I n theta. Okay, so if you see this is the geometric series with the initial part, the initial one is this guy, minus I n theta. And then there's a ratio, right? So the ratio is exponential minus exponential I theta. So it's 1 minus exponential I theta. And then 1 minus exponential I theta times the number of terms, which is 2n plus 1. Okay. And after you do some manipulation, which is just cumbersome calculation. So let me just write down the results. So it will be sine of half of 2n plus 1 theta divided by sine of theta divided by 2. Okay. So this guy is called the Dirichlet kernels. Dirichlet kernel. Okay. So it's called Dirichlet kernel. And so this is the result. So we just play around with this formula. Okay. Hmm. Okay. So the goal is to compute this. So it's 0 to pi, but it's the same, right? It's negative pi to pi. So we are gonna to show the following. We just say we write down f of x and the sine of half of 2n plus 1 x divided by sine of x divided by 2 dx. So the goal is that we want to show that when n goes to infinity, then this guy looks like delta function, right? As we just say. Right, so this is the goal we want to prove. Actually, we just need to prove that it's a 2 pi f of 0. So this is the same. It basically proves that exactly the same thing. Just take 1 over 2 pi here, and that you prove this. Okay, because now theta you just when you do the integration of theta, you just theta just put 0. Okay, so this is the goal we are gonna to prove. Right? This just we just take a limit when n goes to infinity, then this limit becomes the that because exponential ions x n from negative infinity to infinity. Okay, so how do we prove it? Now we use Riemann-Lebesgue, right? So notice that this function is not a well-behaved function because and when x is 0, this is not well-defined. Okay, so if you directly use Riemann-Lebesgue lemma, right, it tell you that oh this guy is 0. Sorry, but when x equals 0 is not well-defined. So let me just write g of x to be when x is non-zero is 0. When x 0, let me just write as a sine of 2m plus 1 divided by x divided by sine of x minus 2. And the minus the same thing, minus x divided by 2. And the sine of half of 2m plus 1. Sorry, this is it will be complicated. X. Okay. So simple speaking, I just write down another term to cancel the cancel x equals 0 part. Okay, so you're very you can easily prove the following. So you can easily prove when limit x goes to 0, then the g of x is well defined. Okay, because the singularity is cancelled by I adding an extra x over 2. You can prove it using the L'Hopital rules. You just yeah, you just write down the L'Hopital rules and you can prove it. So so that means right, so that means that G is a well-defined thing, right? So or maybe G is yeah. So now all I need to do is that I can replace. I know I can replace that. I can use Riemann-Lebesgue lemma. So I know Riemann-Lebesgue. Now Riemann hypothesis. So it's Riemann-Lebesgue lemma. So this f of x. So basically I know the following. I know that limit n goes to infinity, that pi, negative pi to pi, is sine of 2m plus 1. I can replace this by another. Right. So this is by Riemann-Lebesgue lemma. Now because this function is well defined at all x, even for x equals 0. Okay, so since limit is true, so I can replace this guy to this guy. Okay, so now I know I just so I need to only need to worry about this f of x times this thing. X to dx. Right? So I changed the original one to this one. So I care about the large and behavior of this function. Okay, so now you can see oh it's a sine divided by something, right? So you can use the complex integral. Okay, so rest of proof is just very simple. So let me just quickly go through. Maybe let's change it to another page. So let's consider this f of x sine of f of 2n plus 1 x dx. So we do y of 2n plus 1 half of x, right? So we got 2 of uh no let's say no matter f of x, let's say y divided by okay 2n plus 1. And this is basically sine of y. So this is the x dx. There's a linear scaling, so it's this. And then when x is 2 pi, you get something like that. Okay. n goes to infinity. Okay, so when n goes to infinity, that maybe you need some technical input, but you can see that when n goes to infinity, right? This integral become a whole integrate. So it's and this guy I can pull it out, right? Because 2n plus 1 is on the denominator, so it's basically f of 0 times 2 and the sine y divided by y dy. And then this is pi. Because it's pi over 2, but from 0 to infinity is pi over 2, but from negative infinity to infinity is pi. So it's basically 2 pi f of 0. I'll finish the proof. Okay, so this is somehow like the so-called Dirichlet, the kernels, and you can go Wikipedia and find actually the proof is basically exactly the same thing that I just talked about. Yeah, so this is actually built as somehow like the foundation of why this first series in the work, and it's somehow like deep, right? It's not a non-trivial thing that you just write down C and you just plug it back, then you expect to be the same thing, right? So hopefully this video that provided a gap, sorry, not provided a gap, which is fulfill a gap. Okay, see you guys in the next videos. Oh.